Thank you. Well, I don't expect that this talk will beguile you to my way of life, but I will try my best to make X-ray imaging interesting to you. So X-ray imaging, first of all, there's a few things you need to know about physics in general to be able to understand X-ray imaging. First is what an ion is. An ion is an atom that, in which the total number of electrons do not equal the number of protons. So there's a net charge for the atom. Radiation is a process in which energetic particles, either particles or energy waves, travel through space or medium. And X-rays is a type of ionizing photon radiation. So making use of the two definitions we've given so far, that can pass through a significant thickness of tissue before being absorbed. It's a type of radiation that can transit the material a good distance before being absorbed. That's very important in imaging, because if all the radiation is absorbed before it gets out the other side, you don't have an image. So, and what is radiography? Radiography is a shadow image of material density that can be made with X-rays. So we're going to try to produce an X-ray image today, at least virtually on the board. And to do so, you have to understand how X-rays are first produced for the task of doing X-ray imaging. So I'm going to use these pre-drawn drawings that are actually horrible to show you that what you start out with is an electron beam, which is produced by heating up some material and then applying really strong potential to the electrons so that they accelerate and pick up a lot of kinetic energy. And you just slam them against some piece of tungsten material or metal, usually tungsten, so that they release their energy in many different ways, including producing X-rays. So that X-ray beam is actually a kind of a broad fan of X-rays, and you have to do some filtering and collimating on it, and you shine it through your patient or object, and then you do a shadow image on the far side. Now, a little bit more detail on what that X-ray, those X-rays look like, specifically how much energy they get, and exactly what kind of interactions you see when the electrons slam into the tungsten. So when you have electrons, which is another type of radiation, and it's an ionizing radiation as well, because it can cause ions in a material. So when you have electrons, high energy electrons slamming into material, there are three types of interactions that can occur. The first type of interaction is called a collision interaction, which is the most common, and it results in heating of the material. It's a collision between that electron and the other electrons in orbitals around in the atom. But it's not enough to cause the ionization of those electrons. It will just cause vibrations of the atoms, which then heat up the material. The second kind is an ejection of an interorbital electron, so that is an ionization. And that produces characteristic X-rays. If we look at the spectrum of energies coming in the X-ray beam from this tungsten target, we get these little spikes, which are the characteristic X-rays. And finally, you have a broad band of X-ray energies resulting from something called Bremsstrahlung, which is German for breaking radiation. And it basically is when the nucleus is involved in changing the direction of the electron. And when you change the direction of an electron traveling, you're accelerating it, and it shoots off some energy in the way of a photon. So you produce a broad band of energy. So this broad band of energy, then, is what comes out of our tungsten target from this X-ray tube. And we filter this. And why do we filter it? Is because the low energy photons won't really make it all the way through the body. The low energy photons will just get absorbed and not be useful to the imaging. So we want to kind of remove that a little bit. So we filter the low energy photons out first with some filter. And then we use the high energy photons to irradiate the body. Now, the way I've drawn it over here, we have a simple projection image where you have a patient, we shadow image the patient. And then and another option is to actually project at many different angles. And then you can do what's called reconstruction or tomographic imaging, where you have information about the projection in different directions, and you use some sophisticated math like Fourier analysis, and transform that data into an actual 3D image, or in this case, a 2D slice of a 3D object, which we can scan through the patient to build up a 3D image. This whole process is aimed at trying to get information about what those X-rays are doing as they go through the body, which is being absorbed. And how often those X-rays are absorbed depends on the density of the material, also depends on the energy of the photon. But in any case, the general formulation is this exponential that you integrate through the body, and you also have to integrate over not just distance, but also energy, since this is a multi-energy spectrum. So there's lots of corrections to this equation, and it's not justice for me to just write this one little equation up and say this is all we do, because there's a lot of things that go into building a patient imaging system, a lot of corrections that I'm not going to have time to discuss today. So, and then with that, I think I'm going to just sum it up with just saying that X-ray imaging is actually one of the most common forms of imaging methods done in the medical industry, and you know, I bet you every one of you will probably have one unless you absolutely object to it before the time you have passed on. So it's a good thing to know about, because it can itself be a source of health issues, a health concern to some people, because X-rays themselves can be detrimental to health if you get too much of them. But at the levels of doses that we usually see in the medical industry, they're fairly benign. So with that, I thank you.
William wrote this morning and said that he has